ounces, and so our number is going to get smaller. And so we're starting with 12.0 grams. We know the relationship. We're going to do something with 28.34. Do I want to multiply or divide?
Divide.
Divide. I can take 12 and multiply it by that number, but it's going to get larger. And that's not what we want to do. So I need to take 12 divided by 28.34 to get my answer. For 2, 3 ounces. Good on those? And so I wrote, and the slide has 0.423 ounces. That is the correct answer. Why did we not write 0.42? If you put that in your calculator, it's also going to tell you 0.4234. Why is that the answer and not that or that? How many people have taken chemistry before at some level? Do you remember why that's the correct answer? Significant figures. How many people have nightmares about significant figures? If you don't now, wait. You all got to sleep tonight. Sig figs. We abbreviate significant figures to sig figs. When you get a number answer in science, you have to think about sig figs. This actually happens. You spend hours working on a problem. You're not going to spend hours or a week writing a lab report, but you may get stuck on a problem sometime this semester. You work on it, you work on it, you work on it, you finally get it. You're so happy with yourself. You turn it in, and I mark it wrong because you forgot about sig figs. Luckily for you, I don't completely mark something wrong if you get sig figs wrong. I take just a tiny, tiny little portion of your grade off, okay? I care more about what you did than your sig figs. And after a couple weeks in here, I'll stop even marking off as sig figs at all. I'm only going to grade sig figs on problems that are specifically about sig figs, okay? Later on when we do, so let's say you do a density problem here, I don't really care about sig figs. If I can get you to do the density problem correctly, that's a win for both of us, okay? But if I ask you a question specifically about sig figs, or I give you a density problem and then tell you your answer must be in the correct sig figs, then you need to do sig figs, okay? So just be on the lookout for whether you need to do them or not. So what are these little devils? We have rules that tell us whether a digit is significant, okay? Significant figures exist, and so that if you report a measurement, say you publish a measurement, or you give me your number, it tells me how confident you are in your measurement. The more decimal places that you give me, the more significant figures that you give me, that means you're more confident. If you can only give me one decimal place, that means you're not very confident beyond that. Okay, that determines how small of a measurement you are able to take. First of all, our first rule is the simplest. Any digit that is not a zero, we say is significant. So, in the number 435, how many sig figs do we have? 3. Because none of them are zeros, they all count. And so we have 1, 2, 3 sig figs. And it doesn't matter what place they are in. It doesn't matter really that it's 435. we take each individual digit separately. The 4 is not a 0, it's significant. 3 is not a 0, it's significant. Same as 5. So we have 5 significant digits, and so we have 3 sig figs. If we have a 0, and it's between 2 non-zeros, it is significant. And it doesn't matter where the decimal point is. So we have 405. That 0 is between 4 and 5, so that is 3 sig figs. If we have 40.5, that 0 is still between the 4 and the 5, so we have 3 sig figs. If we have what we call leading zeros, they are never ever significant. And a leading zero are zeros that are to the left of the first non-zero. And so here, our first non-zero is the 4. We go from left to right. The first non-zero is 4. And so these zeros are leading zeros. They are not significant. So again, we have 1, 2, 3 sig figs. Over here, we have 1 leading zero. So we have 2 sig figs. Trailing zeros are significant if there is a decimal place or decimal point written. So this is the only one that's a it depends rule. So if we look at this number, this is 400 with a decimal point. It looks really weird that we have a decimal point and nothing after it, but that is correct. So these are trailing zeros. They're trailing zeros because they are to the right of the last non-zero. We only have 1 non-zero, or 4, and these zeros are to the right of it. So if there is a decimal point written, trailing zeros are significant. If there is no decimal point written, they are not. So how many sig figs are in that 400? 3. 400 point has 3. If I write 400 without the point, 1. They're still trailing zeros, but because there is no decimal point there, trailing zeros don't count. If there's a decimal point anywhere, trailing zeros count. So how many sig figs are in that number? 5. We've got 405. That 0 is between 2 non-zeros. These are trailing zeros, but there's a decimal point. How many sig figs are in 26? 2. How about that one? 7. We got 5 non-zeros. Those are easy. These are trailing zeros. So it depends on whether there is a decimal point. And there is. It's right there, and so they count. Regardless of where the decimal point is, it is there. And so we have 5, 6, 7. How many in this one? 4. These are leading zeros. It doesn't matter whether there's a decimal or not. If they are leading, they don't count. So we have 1, 2, 3, 4. These are scientific notation, which we're coming to. But when you look at scientific notation, in sig figs, all you care about is the number in front of the times sign. So even if this doesn't mean anything to you yet, just look at the 9. How many sig figs are in that? 1. Now just look at that. How many sig figs are in there? 8. 1, 2, 3, 4, 5, 6, 7, 8. The 0 counts because it's in the middle. And it's to the right of the decimal point. That, you don't even have to go that far because it's between non-zeros. Unfortunately, though, we don't just stop with our measurement. We take a measurement, and then we do something with it. And so we have to have rules on what to do with sig figs in math. Multiplication and division is pretty straightforward. Whichever number started with the least number of sig figs, that's how many sig figs your answer has. So how many sig figs are in 2.06? 3. How many are in 4.3? 2. What's less, 3 or 2? 2. And so your answer will have 2. If you put this into your calculator, it's going to tell you 8.853. How many sig figs does that have? 4. We can only have 2 though. So we have to round.
8.9.
We start from the left and we count until we hit 2. When we hit 2, we have to stop. So we got 1, 2. We have to round here. The rounding goes by the rules you've used your entire life. So how would you round that based on rounding it across the line here?
8.9.
8.9. The 5.3 would round up. You would get 8.9. How many sig figs should your answer have here? 2. This has 2. That has 3. So your answer will have 2. What is 6 divided by 3? 2. And so if you put that into your calculator, you are going to get 2. How many sig figs does that have? 1. We're supposed to have 2. How can I make that, looks like a Zorro Z, but how can I make that 2 have 2 sig figs?
Turn it into 0.0.
0.0. If I add a 0 onto the beginning, that doesn't serve any purpose. That's a leading 0. That doesn't give me any more sig figs. If I put a 0 onto the end, that's 20. 20 is a different number than 2. So you can't have 20. But if you go 2.0, that's still 2. 2 and 2.0 are mathematically, numerically the same quantity, right? But now we have 2 sig figs. So this is a good example, I think, of showing how confident you are in your number. If I measure something and I say it is 2 centimeters, and then Carla measures something and she says it is 2.0 centimeters, who are you going to believe had the better measurement? Carla. Because she can measure it to that point. I can only measure it to one number. She can measure it to a decimal place, and I can't. Look at this one. How many sig figs should your answer have here? 1. Every single one of you can do this problem in their head. What is the answer? 4. If you put that into your calculator, you're going to get 4.48 something, 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 but it doesn't even matter. You can only have 1 sig fig. That's going to round down. Your answer is 4. And so by multiplying by 1.123456789, you accomplish absolutely nothing. You took 4, multiplied it by a number, and got 4. How about this one? How many sig figs should your answer have? 2. What is 5 times 2? 10. How many sig figs does that have? 1. How can I get it to have 2?
0.0.
Like that. You have to stop there. It looks weird, but it's correct. If I do what seems natural and put that there, now it's 3. You have to leave that decimal point hanging there. Your OCD is going to drive you crazy. It just bugs you to see that, right? But you gotta leave it. Addition and subtraction is more of a pain. Okay? Technically, in order to do this with sig figs, you need to do addition and subtraction longhand. How many people have done addition and subtraction like that in the last 10 years? Probably 1.
I had to do it for pre-chem. You managed to do it out.
Oh, for the same reason? Okay. Has anybody done this not for the purpose of sig figs? Probably not. But this is how this works, okay? So for addition and subtraction, we line up our numbers based on decimal points. And then we're going to draw a vertical line to the right of the end of the number that ends the soonest. When I mean the soonest, I mean going from left to right. If I go from the left to the right, I'm going over, that number's done. These numbers continue on, but that number's done. And so I draw a line there. I do my addition and subtraction like I always would in first grade. Get my answer, completely ignoring the line. But now I have an answer with some numbers to the left of the line, some to the right of the line. And I round based off that line. So in this case, I need to get rid of that 2, 6. Anything to the right of the line has to go away. And so what would you round this number to?
46.
4690.5.
4691.
Stop. 4690.5, and you stop. You leave the line. Anything to the left of the line stays unless that number has to round up when you get rid of that. And so for addition and subtraction, it's not about how many sig figs you start with. It's actually about how many decimal places you start with. And so the number of sig figs can change. So here we started with 6, 2, and 5. Our answer has 1, 2, 3, 4, 5. If I add 2.0 and 0.2, how many sig figs does that have?
2.
2. How many about that one?
1.
1. But I line them up. Let's say I want to add them together. I line the decimal places up, and I add them. I get 2.2. Now I have to figure out where to draw the line. Where do I draw the line in this case? Where does, going from left to right, where does the first number end? They both have numbers here. They both have numbers here. Neither of them have numbers there. And so I draw a line there. My answer is 2.2. Even though one of my numbers started with 1 sig fig, my answer has 2. And so it's just a matter of drawing the line. You gotta draw the line. Another way to do this without doing this longhand is you can, in fact, put it into your calculator. Somebody do me a favor, put that into your calculator and tell me what you get.
It has scientific notation.
I have negative 928,331.55.
Going forward, scientific notation will be fine, but for this example, I need the regular ones. Thank you. Negative 928,331.556. Thank you. So that is what your calculator gives you. You didn't do anything longhand. You have to figure out, though, where to round that.
After the second line.
So you're saying there,
Yeah.
right? Where did you get that spot from?
Because 4.36 is like.
Correct. So she looked at these three numbers and which one has the fewest decimal places? That one has a bunch, that one has 4, that one has 2. The least is 2, and so my answer can only have 2 decimal places. And so what would you report as your answer here? 0.56. So negative 928,331.56. That's going to round up to give 0.56. So most likely, that is the way you would do it on a quiz or an exam, because you probably don't want to do that longhand. You spend the entire time doing it. Okay, let's take our break now. We'll start again at 7:30 on that clock. So it's about 10, 11 minutes.
Can I go turn my hair real quick?
So again?
To the water fountain?
Yeah, we're taking a break.
Alright, cool beans.
I moved your camera chair by accident.
It looked like everybody was able to do the Wiley homework. I see a grade for everybody except the one person that we're working on the issue. Is there anybody that has a grade but yet still has an issue that needs to be fixed?
I don't know if anyone else did, but it took me like 3 hours to problem.
What?
Oh, okay. So just give me this is what I'm loading.
Yeah, everything else on my computer, like the sanitary page and everything else was loading in Canvas, but that website wouldn't load.
Unfortunately, yeah. It normally works, but I don't really feel well. I was talking to somebody. When they have issues, I get an email telling them that there's issues, and they have issues every other day. And so unfortunately, it was just when he was trying to do it. If it keeps having problems, we can work on it. But it was probably just that one. next thing we have is scientific notation. My suggestion, if you have the calculator that you'll be using this semester with you, get it out so you can be comfortable doing scientific notation in your specific calculator, because they all work a little bit differently. So we use scientific notation for numbers that are very large and very small. It allows us to take that number and put it into a more reasonable format. You have 15 quadrillion. You don't want to write out all those zeros. Scientific notation will let you do that. If you have a very, very, very tiny number with 0 point and then 12 zeros and then a 2, you don't want to have to write out all those zeros. So scientific notation will let us skip them. It has a very specific format that you write numbers in. There is a number times 10 to another number. So this C here is just what we call our coefficient. C is for coefficient. And this is going to be a number 1 to 10. It has to be at least 1. It can't be less than 1. You can't have 0.9. It has to be at least 1. And it has to be less than 10. It cannot be 10. You can have 9.99, but you cannot have 10. It has to be between 1 and 10. And n is an exponent, but it's 10 to the power of n. And it has to be a positive or negative integer. What is an integer? It's a whole number. You can have 1, you can have 2, you can have 3, you can have -1, -2, -3, you can have 0. You can't have 1.1, you can't have -2.8. Okay? N has to be a whole number. So you end up with a number times 10 to another number. So we can go from normal notation, just regular written out numbers, to scientific notation, but we can also undo scientific notation. If we're going from normal to scientific notation, we have to figure out what C is. That's the first step. We are going to move the decimal point from wherever it was start with to the right of the first non-zero digit, and so that we have something point something. Okay, we're going to, wherever the decimal point is to start with, we're going to move it to the same spot always. N is going to be however many places you had to move the decimal place to get to where you stopped. If you move the decimal point to the left, N is going to be positive. If you move the decimal point to the right, it's going to be negative. So let's start with this one. We have 3,245. Where is the decimal point currently?
Behind the 5.
It's after the 5. We don't write it, but it is there. We need it to be after the first non-zero. The 3 is our first non-zero, so we need to get it here. How many places do we need to go to get from here to here? 1, 2, 3. We moved 3 places. N is 3. Do we move to the left or right? Left. And this slide said if we move to the left, N is positive. And so we have 3,245. We're going to go 1, 2, 3. We now have 3.245 times 10 to the third, and it's positive 3 because we went to the left. This other one, this one is larger than 1. This one is much smaller than 1. So where does the decimal point need to end up to begin with, at the end? Between the 3 and the 2, it needs to be here. So we have to go 1, 2, 3, 4, 5, 6 places. So I have 3.245 times 10 to the 6th. Is it positive or negative 6?
Negative.
Negative. We moved it to the right, and so it's negative 6. Don't be shy about counting the places. Yeah,
I
right.
draw. If I really
If
miss
you-
it, I draw. and you-
Yeah, so if you're on paper, don't be shy about doing that, okay? Particularly when you have a whole bunch of zeros, it's very easy to miss one or count one twice, okay? If Einstein was sitting in this class with you and he was looking up there, he would probably go like this in the air, okay? There's no reason to be ashamed about doing it. I do it, I hope you will do it, okay? I will judge you more if you don't do it than if you do it, okay? In the end, you want the correct answer. If it makes you look like you're hallucinating, so be it, okay? Do it. Here's another one. Where does the decimal point need to end up when you finish?
Between 3 and 2.
Between the 3 and the 2. So again, we've got 3.245. In this case, we can drop all of those zeros. When you go from a normal number to a scientific notation number, you can't change the sig figs. In this case, though, these zeros are not significant because there's no decimal place. And so we can get rid of them when we come over here. If they were significant, we can't get rid of them. We'd have to go 3.245000000, so on. So here we have 3.245 times 10 to the what?
9.
1, 2, 3, 4, 5, 6, 7, 8, 9. Positive 9, negative 9.
Positive.
Positive because we went to the left. What about the next one? Where does the decimal point need to end up there?
Between 5 and 0.
Between the 5 and the 0, we've got 5.0607 times 10 to the what?
Negative 3.
Negative 3. We're going to move 1, 2, 3 spots, so it's 3. Then because we went to the right, it is negative 3. What about 88?
1 to the left.
We're going to go 1 to the left, from here to here, and so you get 8.8 times 10 to the 1. How about 2.45?
That's good. So it's times 10 to the 0.
Exactly, yes. You got my trick question before I even had to ask it. So, it's already after the first non-zero. We don't have to move decimal place. But if the question says, give it to me in scientific notation, you better have times 10 to the something. There are two ways to think about this. The easiest, the simplest, is to say, well, you moved it 0 places. And so it's 0. Mathematically, why is that correct? What is 10 to the 0? 1. Anything to the 0th power is 1. And you can multiply anything you want by 1. It's not going to change anything. And so you can take your 2.45, multiply it by 1, it's still 2.45. We have 2.45 times 10 to the 0. So, when you put these numbers in your calculator, it's going to depend on your calculator. Okay? For the most part, the simplest, the most straightforward way, although not necessarily the best way, is to just put this into your calculator. The number times 10 raised to the power of something. If you do this, I beg you, please put it in parentheses. If you don't, your calculator is going to do order of operations incorrectly, and you are going to get a very wrong number. Okay? If you're comfortable enough with order of operations in your calculator and scientific notation to know when you do have to put it in parentheses and when you don't, that's fine. Unless you are 100% confident in yourself, if you always put it in parentheses, it will always work out fine. The other option, and to me, this is what I do, it's fewer buttons to push, and it eliminates the need for parentheses, is to use the exponent button on your calculator. It may be EE, it may be EXP, okay? Most likely, if yours has either of those, and you hit that, it's going to give you one small lowercase up capital E. And so it would be like a 5 with a small capital E, and then it will allow you to put in a number. So you put in 5E4. 5E4 means 5 times 10 to the 4th. Most likely, if you put in a big number and it gives you an answer, then it's so big or it's really small, it's going to give you an answer that looks like that, most likely. Not something that looks like that or that. And so you need to know what that means. Okay? If you do this, make sure you use the EE, the EXP, or whatever your calculator uses in place of those. Do not, under any circumstances, use lowercase e. There are probably 2 of those on your calculator. One is just the letter E, and then one of them is a mathematical symbol, lowercase e, which is very, very, very different. If you don't know what button you need to push to get this, please let me know. I'd be happy to help you with your calculator to figure it out. Okay? But if you do this, it ties this together automatically.
So we don't have to put the parentheses.
So you don't need the parentheses. So you can hit 3 buttons, you put it together. If you don't use the E, you would have to go 5 times 10 to the 4th in parentheses. It's a lot more buttons. It'll work, it'll give you the same answer, but for time purposes, that's a whole lot quicker. Everybody comfortable with this? Is there anyone that wants to do more examples of scientific notation? It's okay if you do? Okay. So if you still need help with this, let me know. We can go over more examples, but we're going to move on. We can do calculations with scientific notation. Yes, you have your calculator. Yes, we just talked about how to put these numbers in. And then once you put these numbers in, hit the times button, the divide, and the plus and the minus, that's all the same. Okay? But sometimes you don't need to take the time to put it into your calculator. Sometimes it is really easy. If you're multiplying two numbers in scientific notation together, you break it apart and do it in 2 steps. First, you multiply the 2 coefficients together. That's that number times that number. 4 times the 1.5. That's that, which comes out to be 6. 2 sig figs, so 6.0. And then you look at your coefficients. Sorry, your exponents. We get 6.0 times 10 to the, now we have to figure it out. If you're multiplying together, you take the exponents and you add them together. So 6 plus negative 3 is what? What is 6 plus negative 3? 3. Positive 3, so we get 6.0 times 10 to the 3rd. You're multiplying together, multiply the coefficients, and then add the exponents. If you're dividing, it's very similar, except you subtract the exponents. So you take the coefficients and do the division, just like the exponents, the times 10 were not even there. What's 4 divided by, what is 4 divided by 2? 2. 2, we have 2 sig figs, so 2.0 times 10 to the, now I take negative 2 minus 3, negative 5. Negative 2 minus 3 is negative 5. If we take scientific notation and we raise it to a power, we put an exponent on our scientific notation, we again break it into 2 parts. We take that exponent and we put it on our coefficient, and so we now have 3 squared. 3 squared is 9. Put that in your calculator, you'll get 9. So now we have 9 2 sig figs, 9.0 times 10 to the something. Now we take that square and we multiply it by the exponent that's on the inside. And so it becomes 4 times 2 is 8. So here's some more examples. We got the first one. Is it multiplication or division? It's multiplication. So what do I do with the coefficients? Multiply them together. If I multiply the coefficients, what do I get? .63. And now what do I do with the exponents? Add them. So I get negative 1. 3 plus negative 4 is negative 1. Is that the answer you put on your paper?
No.
Why?
Sig figs.
Sig figs? How many sig figs should I have?
3.
3? How many do I have? 4. So what do I need to do? You can take the 3 off because it rounds down. Is that the answer you put on your paper?
Decimals in the wrong place.
Decimals in the wrong place. It needs to be over here. So we need 3.76. Which direction did I move that? To the left. So what's going to happen to my exponent? What is this going to become? 0. For every place we move to the left, that exponent is going to go positive by 1. Negative 1 plus 1 is 0. If you have your calculator out, just try putting that into your calculator like you're going to not even try to do it longhand. Make sure that you get, it's probably going to tell you 3.76. Anybody get 3.76? Anybody get something different? There's a lot of typing, but no answers apparently.
We got that.
This is just 3.76. Okay. Oh, good. If you're getting 3.76, you know you're doing it right. So here's a division one. What do I do with the coefficients? Divide them. So I'm going to have 2.99 divided by 4.03. What does that come out to be? 0.742. That. So I got 0.742, and now so I have 0.742 times 10 to the what? Negative 3. We take this one, subtract that one. Negative 9 minus negative 6. So you have a double negative there. So it becomes negative 9 plus 6 is 3. that your final answer?
No.
No. What do I need to do? Move my decimal. I need it over here. So it's 7.42 times 10 to the, careful,
We moved to the right, so we have to go
You
left.
missed your negative up here.
Going down, it's like 4.
We're supposed to
Shouldn't
be.
the ex-
Ooh,
Shouldn't it be
shouldn't the three
negative?
be on the
that's negative 3?
Yeah.
Yes, that, yeah, there you go. Thank you.
So now, -4.
Negative 4. For every place we move to the right, we get negative by 1. So we went from negative 3 to negative 4. Do we have the right sig figs? Yes. Those both have 3. Our answer has 3. What about the third one? What do we do with our coefficient there?
Raise it to the 4th power.
We raise it to the 4th power. So what is 7 to the 4th power?
2401.
2401. What do we do with our multiply? So we get 3 times 4 is 12. Now what? Move the decimal. 1, 2, 3. So I have 2.401 times 10 to the 15. So I started at 12, 13, 14, 15. Is that it?
No.
Sig figs. How many sig figs do I need? 1. What do I do with it?
Chop off.
Just 2 times 10. So this is the conversion method that I was talking about before. It's called dimensional analysis. How many people have used dimensional analysis? I like dimensional analysis. I use dimensional analysis outside of class, like actual science, okay? Dimensional analysis is your friend. When we use dimensional analysis, we're following kind of a roadmap. You start off looking at your problem and you say, what are we starting with? Where are we trying to end up? And then you look at what conversion factors do I know? Some of them will be simple conversions, like 1 meter is 100 centimeters, something like that. Some will be things you already know, like 12 inches in a foot. Some of them will be things you have no idea about. So it will be a conversion factor explicitly given to you, or it's on your cheat sheet. So you look at, where am I starting? Where am I trying to get? What conversion factors do I have to use? You'll set up the problem, and then once it's set up, you just do the math depending on where the numbers fell. So the units will tell you where to put each number, and then you just do the math that it tells you to do in the end. So we use a grid method. There are 2 different ways people like to write dimensional analysis. There is the way that the book likes to do it, in the way that a lot of the slides will have it, and then there is the grid method that I learned and that I use. You're welcome to use either one. I find that most students end up using my grid method. To me, it makes more sense. It's easier to follow. It's neater when you write it out. Okay? So here's an example problem. It's a simple one. We need to convert 2 inches to centimeters. First thing you do is you say, where am I starting? I am starting with 2 inches. So write 2 inches. And then you look at the problem and say, what unit am I trying to get to? In this case, it's centimeters. So I'm trying to get from inches to centimeters, and as I do that, the numbers will follow. You don't have to worry about the numbers. The units will tell you what to do with them. So once you write your starting number, just write your first set of boxes, your first grid. In dimensional analysis, whatever unit is on top here has to go there. You will never not put that unit there. And so just by knowing where you're starting, you automatically know what unit goes there. So this is a one-step conversion. Every set of boxes you go is one step. When you put a number on top of another number like this, they have to be equal to each other. That is a conversion factor. These two things have to be equal. So we're starting in inches. We're trying to get centimeters. When we finish our grid, we need centimeters to be in the top right corner. If we can do it in one step, great. If we can't, we need to keep going until we have centimeters in our top right corner. The unit in the top right corner is the unit of your answer. So if you need centimeters, and centimeters is not in your top right corner, your answer is not in centimeters. So once we have this, we have to think, what relationship do we know? What conversion factors do we know involving inches? In this case, we're given this one. You also know that there are 12 inches equals 1 foot. But we want to get centimeters here. Do we know the direct conversion between inches and centimeters? Yes, it's given to us. And so I can go from inches to centimeters. The question is now, what numbers do I put in? I just take those numbers. 1 inch is 2.54 centimeters. I have centimeters in the top right corner, so I am done setting up the problem. Once you're done setting it up, you take all of the numbers on the top, multiply them together. And so what we have is 2 times 2.54 equals 5.08, correct? Someone with a calculator or someone else who did it in their head? Okay. So the top is 5.08. Now we do the same on the bottom, but we only have one number. This box here will always be empty. We only have one number, and so it's 1. 1. So we did that that math to get that number. We did that math. 1 times nothing equals 1.